Okay, question 5 is a little bit more tricky. Part A starts off easy, but it asks you what polarity of plates A and B. Now it tells you the electrons are deflected towards A. Electrons are negative, which means plate A must be positive to attract them, and plate B therefore must be negative. So it's point Q, and the line RS is 300 millimeters from the left-hand side of the plates. What is the electric field strength at this point? It tells us the electric field strength between those two plates is uniform, which means realistically anywhere between those two plates, we always put the field strength showing what direction a positive particle would feel, a force will be going down the ways. So our electric field is positive, or going down the ways. It's uniform, constant. The question tells us this. So anywhere in there, it's going to be the value quoted in the question, which is just 2000 volts per meter. Part C then asks us what is the vertical force. So we just use our equation that the force on a charged particle electric field is the strength times the charge. That equation is a little bit like F equals mg for a gravitational field. So we just put in the field strength, which is 2000, times the charge, which is an electron, which is 1.6 by 10 to the minus 19, which gives us 3.2 by 10 to the minus 16 newtons. Part D. There's an easy way and a hard way of doing this. Let's go through the easy way. So we're told that a particle enters these plates. I'll just get rid of the field lines. Enters between these two plates and it's going to be attracted towards A. So it's going to take that kind of path. Okay, so initially it's traveling horizontally. Its path is going to change, and we're told that at the end of these two plates it has an upwards displacement of 16 millimeters. Okay, now that is 800 millimeters, okay, from there to there, and we're asked, okay, well, what will happen at point Q? Here you should see the displacement is going to be less in there. That is 300 millimeters along. Now we're looking at vertical displacement, so we're really interested in the vertical displacement here. So just looking at the vertical components of each of these, the vertical velocity at the start is 0. It will have some constant acceleration. Let's just call it A and leave it as A. We don't even have to work it out. And if we call the time taken to get from here across to the end as T2, and we'll then just put a little subscript 2 in this displacement to say after time T2 the displacement is 16 millimeters. So A is constant. We can then use the equation S equals U T plus a half AT squared, but U 0, so that kind of boils down to a half AT squared. So really what we're saying is the displacement is proportional to the time squared that it takes to get from one side to the other. Now, just looking at ratios, if we call this time to get to 300 millimeters T1, the horizontal component, if we look at it now, velocity is constant. It's not being sped up to the right or slowing down. Therefore, what we should be able to see from that is T1 is going to equal 3/8 of T2, because it's 300 millimeters to T1 and 800 millimeters to get to the end. Then, because displacement is proportional to T squared, if we compare how S1 would compare to S2, the time is 3/8, but the displacement is proportional to the time squared, so S1 will be 3/8 squared of S2. Putting in your values gives you that S1 will be 2.25 millimeters. Now, if you got that, well done, because that's a tricky question. There is another way of doing this, which is you use this force here to work out the acceleration on our little electron. By using that, you can then go and work out, using the displacement here as well, work out what T2 is. Using that time and this distance, you can then work out the horizontal component of velocity. Using that, you can then work out what T1 is, and if you know that time, the acceleration, you can then work out S1 using S equals ut plus a half at squared vertically. It takes you way more time. It's much easier doing this question using proportionality than doing all those equations.